Today we're going to take a look at section 4.3, which is greatest common divisors and least common multiples, but we're going to do the divisor part today. We'll do the multiples part next class period. So to start with, we're going to define what a greatest common divisor is. So greatest common divisor, or greatest common factor is another word for it, is the greatest whole number that divides all the numbers in your set. I'll just go ahead and read the next one too, and then we'll talk about that one. Relatively prime. Relatively prime are two or more numbers whose greatest common divisor is 1, i.e. they have no common factors other than 1. Okay, so let's go back to the GCD, or the GCF, if you prefer. What I want to make sure that you understand is that it is, in fact, a divisor. So divisors are almost all smaller than the number that we start with. So if I want a divisor of 100, it can't be 105 because it's bigger, right? So divisors are typically small. Maybe not super small, but they're smaller than what we started with. Sometimes people get confused because it uses the word greatest. So greatest is an adjective talking about the divisors. It's not talking about the number being excessively large. Does that make sense? It's just the biggest number that divides the number we're talking about, or the group of numbers we're talking about. Relatively prime. We've actually seen this concept. I think I did a really good job this semester of not using those words yet. Have you heard me use the words relatively prime? I don't think I did because I was trying to check myself the whole time. Where have we seen this idea of relatively prime? Two or more numbers whose greatest common divisor is 1.
The rules.
Say that louder.
The rule, the two pair, like, I don't know how to describe it, but you know what I mean.
I know you know. Can somebody help Katie out? Michaela, you look like you might know.
5 times 2 equals 10, so those two numbers, they don't have a common factor.
Yeah, that was an example that we just did, right? So looking for what 5 and 2 have in common in terms of their list of multiples, and we said it was multiples of 10. And the reason that worked was because 2 and 5 don't have anything in common. So when two numbers don't have anything in common, they're called relatively prime. So that divisibility rule that we had for 6 that worked only because 2 and 3 don't have any common factors is because 2 and 3 are relatively prime. Okay? And the numbers don't need to be prime to be relatively prime. Right? Like 4 and 9, neither one of them are prime, but they're relatively prime because 4 and 9 do not divide by anything, both of them, by anything in common other than 1. You guys with me? Okay. We're going to look at several greatest common divisor methods. And just kind of like when we looked at the addition and subtraction methods or multiplication and division methods, some methods work better for some sets of numbers. Some work better when numbers are small. Some work better when the numbers are larger. And some work better depending on what's coming next in the material you're teaching. So if you're working almost in like that, middle school or early middle school kind of area where eventually you're going to have to be breaking down factors with variables in it, you're not going to want to use this intersection of set methods that I'm going to sort of show you right now. It just doesn't make sense for that context. So some of them are context specific, but I want to show you several of them. Some of them can be utilized really, really with young children. So intersection of sets method. The first thing you do is you list the divisors of each value, and then you find the biggest number in the list. And that's it. It's a 2-step process. This tends to work well when the numbers are smaller and you don't have a lot of divisors. It tends to work well when you're working, honestly, when you're working with numbers that just don't have a lot of divisors, period, even if they aren't small. So they're easy to make lists of. Or familiar numbers, too, from numbers that you're easy to find the divisors of. So my example, as you can tell, uses something that your numbers you're familiar with, 12 and 15. All right, so if I were to look at the greatest common divisors of 12, what I want to do, 12 and 15, what I want to do first is I want to list all the divisors of 12. And remember, we've done this before. They occur in pairs. So somebody give me a pair of numbers that are going to divide 12. Okay, so I'm going to start with 1 and 12, and then somebody said something else. What? 2 and 6, and then 3 and 4. And then I run out of space between the numbers, right? I went 1, 2, 3. I can't do 5 because there's not a number that divides by 5. And then after that, I'm wrapping, in fact, I'm already wrapping down and below my list. So this is it. And then we have 15. Oops, I didn't mean to do that. 1 and 15. And 3 and 5. Okay, if you write them in pairs, you make sure you don't miss anything. And what you're wanting to do is you're wanting to look for the number that's the biggest that they have in common. Intersection, right? Like we did intersections in the past. What is the biggest number they have in common? 3. That's it. So the GCD is 3. That's it. That's the intersection of sets method. Make sense? Okay. This method tends to work better when the numbers get larger, and it also blends and works its way really nicely into some of the algebra concepts that you do later on. Prime factorization method is to construct the prime factorization of each number, which you know how to do. We've done that. Choose all prime factors that they have in common, and then use the smallest exponent between the two sets of numbers, and then multiply it all back out. Okay, can I switch? Okay, so yeah, you see some bigger numbers now, right? 400 and 360, and I don't know about you, but I would not want to do this with the last method. 1 times 400, 2 times 200. This would take longer, right? Doable, it would just take longer. So we're going to try it with the prime factorization method. Our first number is 400, and I know I showed you how to do factor trees and how to do these division algorithms where it breaks it down, and I'm going to do the division algorithm on this one. So 400 divides very nicely by 2 to give me 200, which divides by 2 to give me 100, which divides by 2 to give me 50, which divides by 2 to give me 25, which divides by 5 and 5. Okay? So if I'm looking at the prime factorization of 400, it's 2 to the 4th times 5 to the 2nd. All right, we're going to do the same thing for 360. 360 divides nicely by, okay, smallest number first, so 2, yeah, 180. And then 2 again to give me 90, and 2 again to give me 45. And yes, it divides by 5, but it divides by something smaller. 3 to give me 15, and then 3 and 5. Okay, so I've got how many 2s? And then I've got a 3 squared, and then 5. Okay, everybody good? Okay, so these are what we're comparing now, is this listing of factors like that. So we've gotten through step 1. Step 2 says to choose the prime factors that they have in common. So what factors do they have in common here? So just the primes first. They have a 2 and a 5. Okay, and then we're going to go back and put the powers on them. It says we're supposed to choose the least power that they have. So if I look at 2s, the first one has 2 to the 4th, the second one has 2 cubed. So how many 2s am I going to have? 3. There's going to be 2 cubed. The first one has 5 squared, the second one just has 5, so how many 5s am I going to have? Just 1. Yeah, so 5 or 5 to the first. And then we're going to multiply it back out. So what is 2 cubed? 8, and then so what is 8 times 5? 40. So our GCD is 40. That good? Okay. The next one is called division by primes. This is probably my favorite. I like the last one just fine. It's got this kind of organized list feel to it, and as you guys know, I'm an organized list kind of person, so I like that kind of a feel. But this one actually blends that organized list into a faster method, and I'm telling you what, I'm all about faster, aren't you? If I can get it done in less time, let's do it, okay? So what we do is we write all the numbers that we're trying to divide in a row, and you could do more than 2 numbers. I think my example has 2 numbers. I think there's another example later we're going to do next time with 3 numbers. You're going to write them in a row, and then you're going to look for what smallest prime factor they have in common that they can both divide by. So like over here, I looked for all the primes, and I just kept breaking them down. Over here, I'm not going to break things down unless they both can be broken down by the same number. Okay, so I'll show you that. You divide the quotients by that common factor, and then you repeat. Rinse, wash, repeat, that kind of stuff. Wash, rinse, repeat, whatever it is. Yeah, you repeat. And so you keep doing that until they have no more factors in common. So we're going to do 410 and 360. So we're going to write the numbers beside each other on a row. And we're going to do the division much like we did the division for the other one. But we're going to ask what small prime number do they both have in common, the smallest prime. And that answer is 2. Smaller, 2. Okay, we'll get to 5, I promise. So what's 410 divided by 2? 205. And 360 divided by 2? 180. Yeah. All right, so do they both just still divide by 2? No. Do they both divide by 3? No. Like 180 does divide by 3, but they don't both divide by 3, right? And same thing with the 180 with 2. How about 5? Yes, I told you we were going to get to that 5, Colton. Okay, so if I divide by 5, what is 205 divided by 5?
41.
41. And 180 divided by 5? 36. 41 and 36. Any common factors? No. You might know that because 41's prime, and you might just know that 41's prime. Even if you don't, you can pretty quickly exhaust the possibilities, right? They're not both divisible by 2. They're not both divisible by 3. They're not both divisible by 5. And then once we get to 7, we've gotten far enough because 36 square root, when we did that square root thing last time, right? 36, if you take a square root 6, and I've gotten too big. There aren't any more. I'm done. So we are done. Here's the cool thing about this. That's your answer. So the GCD is 2 times 5 or 10. Isn't that cool? It's like the last one, but faster.
Yeah.
Got a list, and it's all right there, condensed, and it's really friendly. All right, the last one, the Euclidean algorithm, is quite different than the others. Let's just write in the notes first, and then I'll show you how it works when we do it. You divide the larger number by the smaller one. You divide the previous divisor by the remainder. And then you repeat until you get a remainder of 0. The last number that you divide by, the last divisor, is the GCD. Okay, so this is kind of like when we did divisibility by 11. It's really weird to write down. The steps sound really awkward, but doing it's really not hard. Okay? So, are you ready to give it a try? So I chose 72 and 126, and we're going to divide. Bigger number divided by smaller number. Okay? So step 1 is going to be 126, and we're going to divide by 72. And I'm not doing a division algorithm where I'm dividing down or anything. It's just a one-step division. Okay? So I need you to grab your calculator. This is one of those like, yay, I get to use my calculator. If it's going to help us out here, it's going to be great. How many times does 72 go into 126? 1 time. So whether you're doing it with your calculator or by hand, 72 or 126 minus 72 is, what is it? 54. Okay, everybody good so far? So this is step 1. I did the division. Step 2 says to take the remainder and the divisor and do it again. Okay, the remainder should be smaller than the divisor, otherwise you did the division wrong. So we take the 72 and we would divide by 54. So how many times will 72 go into 54? 1. Did I say it backwards? I'm sorry. How many times will 54 go into 72? My bad. And then what is 72 minus 54? 18. And then I take, again, the divisor and the remainder. Remainder better be smaller than the divisor, or you've done something wrong. How many times will 18 go into 54? 3. And what is 3 times 18? 54. I'm done because I got a remainder of 0. So this 0 tells me that I'm done. And once I get there, the last thing I divided by is the greatest common divisor. So the division, it's not a hard process. It's very veiled. It's not really intuitive about why it's happening, right? Why it works. But the logistics and how you process through it are pretty straightforward division. Any questions on that one?
How does that work?
I think the book has a pretty good explanation for it. It's not something I usually do in class because that's not kind of where we're going with that. But yeah, check your book out. All right, that's it for today. We're going to stop with GCDs and we'll pick up with LCMs next time.